Okay, as promised, today we're going to take up fractals. The first example of which was the Sierpinski triangle. The second example. Second example starts this way. It's actually going to start eventually with a triangle also, but the way I'm going to build it is just one side at a time. Every side's going to look alike, and I just want to tell you what one side looks like. Take a segment and take that segment and remove the middle third of that segment. And in place of that middle third, insert two sides of an equilateral triangle. This is step 0. This is step 1. Step 2. Take each segment of that object and remove the middle third. And in place of that middle third, put in two sides of an equilateral triangle. Step 3, you know the drill. Take out the middle third of each segment. And in its place, put in two sides of an equilateral triangle. Repeat this process forever. 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 What you get in the end of that infinite process is one side of the object we're going to look at, and we're going to take 3 of those and put them together. And get the fractal we're going to talk about. Now, notice what I've done here is simply, I guess, this step. I'm drawing it because I'm not going to sit here and do it forever. I'm going to use this as my sort of icon for this fractal. This fractal has a name, by the way. It's called the Koch Snowflake, named after the German mathematician who invented it, Ludwig von Snowflake. So, the Koch Snowflake is our fractal. The 2 questions we want to ask about it, which we're going to answer with infinite geometric series. The 2 questions are, 1, what is its area? 2, what is its perimeter? We'll talk more about fractals later today, tomorrow, the next day, etc. But one of the things we found with the Sierpinski triangle is, essentially, the Sierpinski triangle had no area. When we removed all those regions, the area of the Sierpinski triangle came out to be exactly 0. So one of the things you're going to find about fractals is they always, I'm not going to say it like that. They tend to have very surprising properties, very paradoxical, very unexpected properties. We don't expect things to have area 0. So the questions we want to ask about the Koch snowflake are, what are its properties? What's its area? What's its perimeter? That is to say, when we add this little bit, and then we add these little bits, and we add these little bits, how much area is added? How much more is the Koch snowflake than the original triangle? Say the original triangle is area 1. How much got added? How much got added? How much got added? Similarly with the perimeter, how much got added? 1/3 was removed, 2/3 was added. 1/3 was removed, 1/3 was removed 4 times. 2/3 was removed, 2/3 was added in 8 times. I'm going to start over again because that was stupid. Take out 1/3, add in 2/3. Take out 1, 2, 3, 4. Those aren't thirds anymore, those are actually ninths. And add in 1, 2, 3, 4, 5, 6, 7, 8 ninths. Take out 1, 2, 3, 4, 8, 12, 16, 27ths. Add in 2, 4, 6, 8, 16, 24, 32, 27ths. Repeat that process ad infinitum. And how long is what we get? I'm going to stop there and ask you to do some calculations. I'm going to ask you to generate an infinite series for the area. I'm going to ask you to generate an infinite series for the perimeter. And then we'll talk about the infinite series that result and how to find their sum. That's all for now. Let's do some math and come back.